at something very important. This abstract says a lot. Contrary to what you probably heard, quantum computers are not faster than classical computers. So everyone opens a newspaper, you read about quantum computers, and quantum computers are doing this, and they're going to revolutionize the world, et cetera, et cetera. It's not true. Okay, it's simply not true. The power of quantum computing is that the quantum algorithms demand fewer operation than classical algorithms. In other words, what can be done with a classical computer, the algorithms demand less, which means that the center, the core, the most interesting thing is the quantum algorithms, not the machines. The engineers will take care of the machines. Don't worry about that. As programmers, as developers, I thought you would be interested in that. Okay. This makes quantum algorithms fundamental in quantum computing. We will introduce a touch of quantum mechanics, 3 or 4 slides, and then the basics of quantum computing, 3 or 4 slides. With that in hand, we move on to discuss several of the most important quantum algorithms. We conclude with some speculations about the future of quantum computing. So it's a short talk. So again, quantum mechanics, quantum computing, then here's all the 7 algorithms, and then the post-quantum world. First, quantum mechanics. So there's 2 ideas in quantum mechanics that you have to know that are fundamental, and they explain why quantum computing is so good, okay? And they have to do with 2 experiments, and I'll explain the experiments. So this is Feynman, Richard Feynman. He's a famous physicist. He wrote a book called Lectures on Physics. Volume 3 is all about quantum mechanics. Page 1-1, that's the first page in the 400-page book. He says this line: we choose to examine a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. So what I'm going to say is literally the center of quantum mechanics. We cannot make the mystery go away by explaining how it works. We will just tell you how it works. Okay, so that's that. And the mystery is called the double slit. The experiment is called the double slit experiment. Double slit experiment, if you've seen it, you've seen it. So basically, you have a light, and the light goes through a wall, and there's 2 slits. Okay, there's 2 slits in the wall. And one of the slits, if you block it, then the other slit, think of lights as waves. The waves goes through, and the waves is going to make a lot of white over here. It's going to be dark over here. It's going to be dark over here. It's going to be a little gray over here and a little gray over here, because the waves go and they come right over there. That's if you have a single slit. What happens if you have a double slit? In other words, we take away this block, what's going to happen? Okay? And what's going to happen is the light's going to go, and it's going to go through both slits, and it's like waves, literally like waves in the ocean. And what you're going to have is something like this. Okay? And when you have waves, if you throw 2 pebbles into a pond, some of the waves are going to cancel each other out. Okay? Sorry, I got to put this away, and so I have to do a dance. You ready? So sometimes you're going to have waves like this. They're together, and in that case, you're going to have very bright shades over here and over here. But sometimes you're going to have shades like this, up and down, up and down, up and down. They cancel each other out. And they cancel each other out means there's not going to be light here, there's not going to be light here, there's going to be a lot of light here, a lot of light here, and a lot of light here. So this is different than you would expect. You would think, oh, there's just a lot of light across from it. No, they cancel each other out. Okay? Now that just means that light's a wave, but let's go further with this. Light can be thought of as a wave, and the waves from each slit cancel each other out. The interference, so one interferes with the other, leads to light and dark patches. Physicists can do this experiment with 1 photon at a time. If this is done many times, many of the photons will land in light regions. None of the photons will land in dark regions. So think of a photon as a little light atom, and you let it go 1 at a time. And you want to know, does it go through here? Does it go through here? Okay? And what they say is as follows. If there's only 1 photon at a time to let go, if there's only 1 photon let go at a time, what does the single photon interfere with? You have to see a picture. Okay? So here's the light source, and it's going through like this. You would expect some light goes here. When you're going, 1 photon is going out at a time. You would expect some go here and some go there. But that's not what happens. what happens is, this is what's observed. And again, you have some bright patches where lots of light shine up, and you have some unlight patches where no light shows up. Now you say to yourself, I don't understand. If you tell me light is a wave, so fine, the waves cancel each other out. But if you tell me light is a photon, and you let out one photon at a time, who's it canceling out with? Okay? And we go back here. Here's the answer, and this is the core of quantum mechanics. The photon splits into two and interferes with itself. It does not go through either this slit or that slit. It goes through both slits at one time. Rather than saying it has position, say it has superposition. Now, this is where you say, I don't believe it. And you're allowed to say you don't believe it. This is where you say, oh, this is where it's not true. And a lot of people didn't think it's true. A man named Albert Einstein didn't think it's true, and a man named Schrodinger didn't think it's true. But it's true. Okay? The photon goes through both slits at one time. This superposition is what's used in quantum computing. Okay, let me show it to you in a second. Okay? In quantum mechanics, many properties, not just position, not just is it going through this slit or that slit, but many other things, things called spin, energy, momentum, do not have a single value. Rather, they have many values. They're in a superposition. When they are measured, when you look at it, they are only seen in a position. Why this happened is called the measurement problem. So the reason why you don't believe in superposition is because you've never seen it, except if you drink a lot of tequila. Drink a lot of tequila, and you can see quantum physics working. Okay. Okay. The point is, when you're a conscious human being or a conscious animal, I don't think any animal's ever seen a superposition, never seen it. So that's a question. Why does that happen? Why is something in a superposition, and then when you look at it, it claps? So that's called the measurement problem, and people argue and discuss it, et cetera, but it's a fact. Okay, so before it's measured, it has many values. It's going through this slit, and it's going through that slit. Okay, this is the main use in quantum computing. This is the main. And so I just want to spend a minute here. For example, we're all programmers. We all know how to search for something in an array, right? How do you search for something in an array? Okay, you look at this position in the array, you look at that position in the array, you look at the third position in the array, et cetera, et cetera. You go through the array one at a time. Okay, now, here's the trick of quantum computing. Rather than looking at one position at a time, go into a superposition and look at all the positions at the same time. Okay? That's what quantum computing is all about. You use this fact that things are can be put into a superposition in order to get this massive parallelism. Okay? So this is what quantum computing is all about. And it is a history about it. I don't want to get to the history. I don't want to get into how the engineers are doing it. I want to get to the algorithms. Okay, so one of the things, and the main special thing about quantum mechanics that's used for quantum computing is this superposition. There's another thing called entanglement, and I'll show you what that's about. Okay, so there are particles, there are things, and they spin. Some of them spin. They spin positively, or they spin negatively, and some don't spin at all. Okay, so think of a basketball. Some things spin this way, some things spin that way. Some don't spin at all. Okay, and what you could do is as follows. Here's an experiment. You have a thing that lets out photons, or you let out any particles going like this. And you put it between two magnets. And you allow the photons to go through. Now the magnets make some type of field, and sometimes you're going to see that some of those particles go straight. That means the magnets don't have any effect on it. So we say those particles don't spin. As opposed to that, sometimes they spin this way, and sometimes they spin that way. They never spin in between. It's either positive, negative, or zero. Okay, this is a fact about particles. Okay, now sometimes you can have a big particle that can decay. So you have like X-rays, they decay, they fall apart. And they fall apart into two different smaller particles, and these smaller particles do have spin. Okay, now there's two possibilities. this one can spin positively and this one can be spin negatively, they have to both spin opposite. Why? Because there's something called conservation of spin. You have conservation of mass, no new mass comes, conservation of energy, conservation of momentum, all these conservation things. What that says is that in the universe, things don't change that much. So if you start off with spin 0, and one of them spins positively, the other one's got to be spinning negatively. Okay, great. Or this one could be spinning negatively, and that one has to spin positively. Okay, now, hold up. You ready? Something else can happen here too. Not something that can happen, something else happens. Let's say this decays and no one's looking at it. There's no measurement going on. No one's checking it out. Then what's happening? Then what happens is this one particle splits, and sometimes this spins positively, sometimes it spins negatively. It spins both positively and negatively. It's in a superposition of spinning. Again, you don't believe in superposition. So I'm trying to get you to believe in this thing, but you don't believe in that. You're a bunch of heathens. Okay, anyways, what it does, it splits, okay? And they spin in superposition. But here's the amazing thing. You ready? Let's say I take this particle, I put it in a box, and it splits into 2 other boxes. No one looks at it. And I take this particle, and I send it to Alpha Centauri. Alpha Centauri is a star that's millions and millions of light years away. It's the closest star to our star. Okay, it's millions of light years. And this one I keep here, again, in a box. I don't look at it, because if you look at it and you're not drinking tequila, if you look at it and you're not drinking tequila, you'll see it either spinning this way or spinning that way. Okay? I don't want to look at it. Okay, good. Now, I have my box with a particle in it. It's spinning this way and that way. That particle is in a star far, far away, and it's spinning this way and that way. Now, one day, a Sunday night, I get bored and I decide to open the box and look. Now, I could see it spinning positively or I could see it spinning negatively, right? But here's the amazing thing. The law of conservation of spin says if this is spinning positively, that one, all the way there, millions and millions and millions of light years across the universe, has to spin, stop being in a superposition, and spin the opposite way of this. Because it has to be like that. That's, as my mother says, that's the way it is. That's the way the universe is. Okay, so this is the amazing thing. The amazing thing is, if you look at this one, that one, and it's spinning one way, that one has to spin the exact opposite way, even though it's millions of miles away. Okay, now you're shaking your head. You don't believe it because you're a bunch of heathens. Okay, I want to tell you something else, somebody else who didn't believe it, Albert Einstein. Okay, he didn't believe it. He used to call it spooky action at a distance. He said this is spooky. He made fun of this. He said this is spooky action at a distance. He says it doesn't make sense. He invented relativity theory. Thank you, Ma. He invented relativity theory, and relativity theory says things far away don't affect each other. So how could this be? How could it be that when I look at this and I see it spinning one way, that's spinning the other way, that stops being in a superposition and go like that? He didn't believe it. But it's true, and it's used in quantum computing. Okay, so let's just talk about how it's used. Quantum mechanics, entanglement. Entanglement is not just a quirky quantum phenomenon. It's a fundamental resource that allows quantum computers to perform computations in fundamentally different and more powerful ways than classical computers. Because the results of measurements are entangled like this, even though they're far away, it's not really far away, but they're just entangled like that, it is what allows the creation of correlations between qubits. I'll talk about what that is, and to give you a computational advantages. It is what allows for the manipulation of quantum information in ways that lead to exponential speedups in certain algorithms. And we're going to go to those algorithms in a minute. Okay, so those two things, superposition and entanglement, that's what gives you the power of quantum computing. Great. So now let's talk about quantum computers. So we finished our quantum mechanics. You did quantum mechanics in 5 minutes. Quantum computing is like this. Here's a classical bit. This is a computer. It's made out of a lot of bits. What do the bits do? They're either 0 or 1. Okay? Now, then you can get into something called probabilistic bits. Things like fuzzy logic or AI type stuff where things are a little bit 0, a little bit 1 here and there. Then comes quantum stuff, and this is called a quantum bit. And what you can be is, you can be in, you ready? A superposition of 0 and 1. Not a little bit 0 and a little bit 1. You can be in both at the same time. Okay, so let me show you how that works. That's using this superposition not for on qubits, on bits. So again, I don't want a bit that's either 0 or 1. I want a bit that's both in some sense. Okay, a bit is either 0 or 1. Switch on is off. So again, we know what a bit is. We deal with it. Electricity flowing or not flowing through a transistor. A metal ring magnetized one way or another way. Okay, so that's what a bit is. A qubit is a little bit 0. I'm sorry, it's 0. This is a complex number, and 1 at the same time. And these complex numbers, C0 and C1, 0 tells you the chances that after measuring in the qubit it will be found in 0, and C1 tells you the chance that it will be found in 1. Okay, so again, we're using this concept of superposition on a bit. No more are we going to have a switch either on or off. We're going to have a switch that's both on and off at the same time. Okay, what happens if you have two qubits? Well, if you have 2 qubits, when you measure them, you have 2 possibilities of what you're going to see. 0, 0, 0, 1, 1, 0, 1, 1. Okay, great. I want to put 2 bits in a superposition. So then you have this. You have some complex number telling you what's the chances of being like this. Some complex number telling you what's the chances of it being 0 and 1. Some complex number telling you what's the chances of it being 1 and 0 and 1, 1. Again, when you have 2 switches, you have 4 possibilities of where those switches could be. And we want to be in a superposition of all 4 at the same time. For a system with n qubits, let's say I have, there's no switches in this room. Let's say I have n switches or n bits. Then there are 2 to the n possible ways they can be found after measurements. So let's go through it. 1 qubit can be in one of 2 ways. 2 qubits can be one of 4 ways. 3 qubits can be one of 8 ways. N qubits can be one of 2 to the n. Okay? To describe n bits, to describe n bits, regular bits, you need n bits. I want to say, okay, here's the state of, here's n switches. I want to describe it. I can say 1, 0, 0, 0, 1, 1, 1, 0, 1. That's n bits that give you the thing. To describe n qubits, I need 2 to the n complex numbers, because I need the numbers to tell me to what extent it's this, to what extent it's that. So that gets already complicated. Let me tell you why. Okay? This exponential growth, you need 2 to the n qubits, complex numbers, was one of the ideas that got Feynman interested in making quantum computers. Feynman said, if you want to mimic a quantum system, you better have a quantum computer. The idea is as follows. Every modern computer has at least 64 bits. Every computer is a 64-bit computer. Imagine a 64-qubit computer. Okay? That would demand that many complex numbers. Okay? This computer, as good as it is, cannot deal with that math. Not even no computer in the world can deal with that. So it's hard to mimic a quantum computer with a classical computer because you need a lot of numbers to deal with it. So you cannot mimic it for anything bigger than 10 qubits or something like that. You cannot mimic it. It needs too much resources. That's a lot. Okay? Okay. Hence, it is impossible to mimic a large quantum computer with a regular computer. Okay, great. This is talking about the states of the system. So a quantum computer is going to be made out of these qubits, and to describe them we need a lot of things, but we want to use them without describing them. Hold on. Okay, great. How about dynamics? How do computers change? So here we have a computer, and what's inside? We have lots of different logic gates. If you've seen it, you've seen it. If not, not. Most of our computers are made out of NAND gates, okay? Because NAND gates can give you everything else. That's fine. and we build circuits with these NAND gate, with these things. We build very nice circuits, and basically we have bits coming in here, and we make adders, and we say if he presses Control and he presses E at the same time, exclusive OR, not that, et cetera, we can do that. And basically, programs are like this. You use your ALU, you have your bits coming in and you have your bits coming out, and that's what a computer program is. Great, that's for a classical computer. I'm not interested, I'm interested in quantum computers. Okay, in a quantum computer, qubits are manipulated by things called quantum gates. I'll show you what they are in a second. A quantum program is going to be a composition of quantum gates. I'll show you in a second. Usually we're going to be okay, so let me just get to the picture. Okay, I'm going to go through this a little bit faster because my attention deficit disorder is starting to kick in. But basically what you're going to have is, this is going to be a typical quantum program, okay, an algorithm. Okay, again, the qubits start out over here, okay, and they go through these. Each one of these boxes tell it a different thing to do, okay? And at the end, so hold on, these H's, they stand for Hadamard, they put things in a superposition. So what did I say? What's the power of quantum computer? The power of quantum computing is you start off, you go into a superposition and you try to do everything at one time. That's exactly what we're doing here. We start off and we put everything with these H's, put things in a superposition. And then we do different operations to them. At the end, we have to measure them. So that's a meter where we measure them, which means we have to collapse the superposition. We need to get results. Okay? And so this is what a typical quantum computer would look like. Of course, I have to explain to you what these operations are and how they change the qubits, but this is exactly what it does. Okay, and it's very nice. By the way, you can start doing quantum computing tonight. First thing, go buy this book. Okay, it helped me pay my mortgage for a Brooklyn house. Ready? Anyway, so this will help you do it. It's a very good book, et cetera, et cetera. But IBM is very much into educating quantum computing. And so they have a thing called Qiskit, Quantum Information System Kit. You can literally type in Qiskit, and you can make your own account, and you can start programming with this. It's not just an online quantum computer. They have videos and they have explanations, et cetera, et cetera. And you can, with like Scratch, you can say, okay, I want an H gate over here. I want to put this gate over here. I want to do this or this, okay? And then you can actually run the program. And you're not running a simulation. This is the amazing thing. IBM has you, what you do is you set up the way you want your circuit to be, and you wait a little bit until they have a quantum computer ready. They upload it to them, and they actually run it on a quantum computer, not a classical computer. Okay, and you can really do this tonight. It's an amazing thing, and you get it. So this is the IBM Experience, whatever. It's a very nice trick. Okay, great. Again, I skipped over a lot of details, and I'm going to skip over a lot of details because we're not interested in how they build quantum computers. We're interested in the algorithms. Okay, so the algorithms. Here's a cute algorithm. It's by a guy named David Deutsch, and it was one of the first algorithms. It goes like this. Deutsch's algorithm deals with a function from 1 bit to 1 bit. Okay? In other words, it inputs 0 or 1, and the output is 0 or 1. Now, if you think of it, there are 4 such functions. Let's go through it. You ready? F of 0 could be 0, and f of 1 is 1. So everything just goes to the identity. Or 0 goes to 1, 1 goes to 0. Or everything goes to 0, or everything goes to 1. Those are the 4 functions you have from a bit to a bit. Okay? The problem asks whether the following thing. Let's say I give you a box, and I say it does, you input a 0 or 1 here, you output a 0 or 1 here. And I want to know the following question. is the function in this box, it's a black box, you can't look inside, is it constant, which means f of 0 equals f of 1, both the outputs go to 0 or both the outputs go to 1, or is it balanced, which means f of 0 is not equal to f of 1. So is it 0 goes to 0 and 1 goes to 1, or is it 0 goes to 1, 1 goes to 0? They're not, the outputs are not equal. That's one question I ask. So again, you're given a black box and you want to know, is it constant or balanced? Okay, so let's go through it. Classically, this demands two function evaluations. How would you do this? We're all programmers, how would you do it? You have a box, you can plug in 0 or 1 here, and you could get out 0 or 1 over there. How do you tell, is it constant or balanced? And the answer is very simple. Plug in 0, see what the result is. Plug in 1, see what the result is. If the results are equal, bingo, it's constant. If the results are not equal, it's balanced, finished. Okay, so you need two function evaluations. I have a pretty picture for this. You start off with no information. You plug in f of 0, and you could either get out 0 or 1. You plug in f of 1, the next one, and here you say f of 0 is 0, f of 1 is 1, it's a constant, they both go to 0. Here you say f of 0 is 0, f of 1 is 1, it's balanced. Here you say f of 0 is 1, it's balanced, constant. So there's the four possibilities. And what you say is, okay, these two are constant, these are balanced, I can answer the question, but I have to run it twice. I have to put data in twice. Great. With a quantum computer, this problem can be solved with one function evaluation. I don't need to do it twice, I can do it once. That's a speed up. It's not a very interesting speed up, but it's a speed up. Instead of running the algorithm, the box twice, I run the algorithm once. Okay? And this is somewhat of the algorithm. Basically, you put things in a how does it work? Very simple. Put it in a superposition. Don't put into the box 0 and then put in 1. Put in 0 and 1 together at the same time. Okay? And then you're going to get out some result. And we're going to have to mush some of the results, whatever, but I only have to do it once. And I get out a totally good result, and it works. Again, it's not very interesting, but and you'll see, we'll get to the more interesting things too. Okay, so that was called distinguishing constant and balancing. Now we're going to do generalized distinguishing. It's called the Deutsch Jose. Deutsch was a guy, and Jose is another guy. Same Deutsch, but different Jose. Okay, so it's as follows. Instead of dealing with a function from 0 to 1, deal with a function with n bits go in and 1 bit goes out. So you have that box, and instead of putting in 1 bit, you put in n bits here. Okay, and you can get out like that. And you ask the same question, constant. Does the same output for all, there's 2 to the n inputs. There's 2 to the n strings of length, whatever. Okay, is there one, is it constant or balanced? Anyways, it's constant and balanced. We'll do this quickly. Classically, this demands 2 to the n, about half of the evaluations. You have to do it until you see if there's any differences. If all the inputs are always outputting 0, then you know it's constant. If all the inputs are always outputting 1, you know it's constant. But it could be half and half. And so you might have to do it a lot. Great. Classically, this demands 2 to the n minus 1 function evaluations. With a quantum computer, this can be done with one function evaluation. So you don't have to do this box 2 to the n times. You could do it with 1. Bomb. That's amazing. How do you do it? Put it in a superposition. Put the input in a superposition. You're going to get out an output, et cetera, et cetera. Okay. We'll do this quickly. So here's the AND operation. Okay, 1 and 0 is 0. 1 and 1 is 1, et cetera, et cetera. 0 and 1 is 1. Okay, consider the following. Okay, now look at the parity of this result, 0 or 1, even or odds. Okay, I'm going to go through this a little bit quickly. So here's the thing. Take two strings, do the AND of both of them, and then take the parity. But the parity basically is telling you is it odd or even the amount of times they're both 1? That's the question. Okay, good. Let S be a secret binary code. Consider the following black box function. Again, takes in n things and outputs 0, 1, defined as f of x is equal to parity of s of x more 1. Okay, so there's a secret code, and you input x, and you do AND of it, and then the parity of it. Doesn't matter. Okay, here's the problem. Given such a function, find the secret s. Okay, and there's a way of doing it. Okay, here I show you how to do it. You need n function evaluations. With a quantum computer, you could do it with one function evaluation. Very nice. Okay, I'm going to do Simon's algorithm a little bit faster. Simon's algorithm is another thing that's faster. All of these are strange problems. They're just not interesting problems. You're saying, oh, can you do this, balance? It just doesn't show up often. But here is the interesting problem. Okay, these three are very interesting problems, and we'll go through this. Finding a needle in a haystack. This is the main thing. It's called Grover's algorithm, and the idea is as follows. What does it mean to find a needle in a haystack? How do you find a needle in a haystack? The phrase, where does it come from? Well, if you have a haystack, and you know you lost a needle in it, how do you find it? The only way to do it is a brute force search. Pick up this piece of hay. No, that's hay. Pick up this piece of hay. No, that's hay. Pick up this piece of hay. No, that's hay. Okay, you're going to have to do it over and over and over. It's not very interesting. It's not very effective. Okay, so that's called finding a needle in a haystack. Let's see what a quantum computer can do better. Okay, this is very important. This algorithm, Grover's search algorithm, deals with a function. Again, it has 2 to the n possible inputs, n bits. Okay, we are assured, promised, that there's exactly one x such that f of x is equal to 1. In other words, you have a haystack of 2 to the n pieces of hay with one needle in it. And what you want to do is go through the things very, very quickly, okay? Go through the things very, very quickly and find that one needle. So you're assured, you're promised that for one of them, one of the inputs, the output will be a 1, everything else, the output will be a 0. So you're actually doing a search algorithm. Again, when I'm searching. There's a person in this room named Anzarut, right? That's you, I could tell. Your father's from Memphis? He was a tzaddik. He was a great man. Anyways, so I knew that because it was on the list, whatever. But the point is, how do I find this person? Are you Anzarut? Are you Anzarut? Are you Anzarut? Are you, et cetera, et cetera, et cetera, et cetera. Okay, until I see a guy who looks like his father. Okay, anyways, so you do it with one. Great. How does Grover's algorithm work? It puts it into a superposition. It doesn't take one output. It doesn't do, you can't do it with one. Classically, this demands 2 to the n function evaluations. With a quantum computer, this can be done with square root of 2 to the n evaluations. That's a tremendous speed up. Not a polynomial, not very good, but that's a tremendous speed up. This algorithm is the one that's used all the time in quantum computers. Okay? I'm sorry, not all the time, a lot of the time. The point is, it's a way of finding things quickly. So you have some chemical thing, you have some DNA stuff that you want to search for very quickly, you have some folding mechanism, et cetera, et cetera. You have some stuff that's working on Wall Street to find some nice database or something result. Searching for things is very quick. It does it a lot quicker than anything else. Okay, most quantum algorithms use this algorithm. Notice the speed up does not take an exponential 2 to the n to a polynomial problem. That doesn't happen. But it takes it from 2 to the n to square root of 2 to the n, which is a tremendous speed up. It's smaller. Okay, great. Okay, next most important algorithm is Shor's algorithm. Okay, and I'll tell you why this is important. Okay, it's very easy to multiply large numbers. Here's a large number, here's a large number. You can multiply them and you get out a large number. In contrast, multiplication of two n-digit numbers is n squared. In contrast, given a large number, how can you factor it? Factor a large number. That's a very hard thing to do. And that's a very good thing that's a very hard thing to do. I'll tell you why. Because when you put in your credit card information to your Amazon, right? When you put in it's hidden with something called RSA. It's hidden with RSA. And the RSA uses that, RSA algorithm uses the fact that it's hard to factor numbers in order to keep things hidden. For example, you have a credit. What's your credit card number? Sometimes that works. Okay, damn. Okay, no laughing next time. All right, anyways, you ready? That's what would happen. You take the credit card, the computer manipulates the credit card number so that only Amazon can read it and only they can check it. Okay? So it's hard to factor numbers. Okay, how do you factor numbers? We're programmers. How do you factor numbers? Well, you divide it by 2, see if it goes in. You divide it by 3, see if it goes in. Divide it by 4, see if it goes in. Okay, and you got to do this till square root of n. That's a lot of work. Okay, and Amazon and RSA uses 250-digit numbers to keep things quiet. Okay, to keep things hidden. So take a 250-digit number, do all of them till square root of n. You're not going to be able to do that. Okay. The fact that it's so hard to factor is the basis of RSA, which keeps communication secret. If there was an easy way to factor whole numbers, RSA would be broken. Okay? Factoring is a natural problem. So the first few problems, they were unnatural, they were strange. Factoring shows up all over. Okay? I hesitate to say this on an open mic, but there are those who believe that there's an organization called NSA, okay, which doesn't stand for anything, and whatever, that they have in their basement a quantum computer which can factor numbers, which means that they can read all your information, et cetera, et cetera. And I just want to say, I'm pro-Trump or wherever I'm supposed to be true. I don't want to start up with anybody. Please let me live. Okay, anyway, so if NSA is running things, I agree with them. The hell with Trump. Okay, next. You got to be careful. Factoring is a natural problem. Okay, great. The Shor's algorithm factors a whole number in polynomial time. It's an n to the 5, n to the 6 algorithm, not hard at all. It can be done with a quantum computer. Again, superposition, again, entanglement. It does it. It's a little bit more complicated, but it's like that. There is no known polynomial algorithm that does this with a classical computer. It was described in 1994 by Peter Shor. This will destroy RSA. Not only will it destroy RSA, but believe it or not, there are companies today that download all the information that they can, even information that's hidden under RSA. In other words, when you bring in your credit card, you send it to Amazon, Amazon gets something. They know how to decrypt that something to get your credit card number. Okay? Well, there are companies that what they do is they just download lots and lots and lots and lots of hidden information with the intent that, you know what, in 5 years we'll have a quantum computer that will be able to decipher this and then we'll use that. Okay? Yes, there are such companies. Do not work for such companies. Be moral and don't do bad. Okay, anyways, but this is an important thing. Okay, last thing, linear algebra, the Haro-Hasidim-Lloyd algorithm. The HHL algorithm solves the most important basic problems in linear algebra. So I'm just going to do this first. A is a matrix, X is a vector, B is a vector. You have something like this. A is a matrix, X is a vector, B is a vector. This shows up all over in all of computing. You want to solve for X. It's hard to do it, usually. You have to do Gaussian elimination, whatever, linear algebra, nonsense, whatever stuff. But in 2009, they came up with a very useful algorithm called the HHL algorithm, and it solves it very much. And this is where you hear these phrases, quantum machine learning. Quantum machine learning is machine learning. Machine learning is all about linear algebra and a little bit of probability theory. Okay? Quantum optimization, you want to optimize problems. So here's the way your things are, here's constraints, you want to do it. Quantum data analytics, quantum BI, it's all done. That's all needs this algorithm very much. It's a very useful thing. Okay, great. Good. I just want to spend 5 minutes talking about the post-quantum world. Okay? So people think, oh my God, quantum computers are going to change the world. I won't be able to buy anything by Amazon because everyone's going to get my credit card information. You have a credit card? All right, good. Okay, you'll show me afterwards. I'll take a picture of it. Okay, anyways, I just want to talk about one other problem that's outside of this that you might have seen before. A traveling salesman wants to visit some city, and I want to show you why you shouldn't be worried. He wants to visit some cities, and he wants to find the shortest path that hits every city exactly once. So here's a nice thing. He wants to go to San Francisco, New York, Miami, Los Angeles, Chicago, and Denver. I put the numbers here in between for the lengths in between. And I want to go to all 6 of these cities, but I want the shortest possible route. In other words, obviously, I should not go from New York to Los Angeles and then back to Miami and then back to San Francisco because I'm going across country back and forth. I want to find the shortest possible route. Okay? For 6 cities, you need to check, well, the first city, you could start with 6 possible cities, 5, 4, 3, 2, 1, 6 factorial possible cities. So you have 720 routes that you have to possibly check to find the shortest. And you have to go through all 720 routes and see which one's the shortest. There used to be a, I don't know if it still exists, Expedia, and Expedia can pretty much do that. You can find, you tell it, I want to go here, 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 I want to drive it, find me the shortest possible route. It'll take 700 possible paths. This computer can do that. This computer can probably check 1 million possible routes in a second. Okay, for n, okay, great. Now let's move it up. For n cities, you need to check n factorial possible paths. Okay, how about for 100 cities? How long will it take for 100 cities? Okay, and the answer is as follows. Okay, think about it. Let's say you're a traveling salesman. You want to go to the 100 most populous cities in the United States. You want to spend 3 days there and sell your widgets to them, and then you want to move to the next city. So you go download Copilot, give me the 100 most populous cities, give me their latitude and longitude. I'd like to go to these 100 possible cities and do that. Okay? Now that I have all the information, I have the 100 possible cities, I have their longitude and latitude, I know how to drive there. Question, what's the shortest possible route? Okay. Now, I'm not asking you what the shortest route is. I'm asking you, how long will it take you to calculate what the shortest route is? The shortest route is not interesting. How long will it take you to calculate how long is the shortest route? Okay, so let's do this. For 6 cities, you have to look at 720 routes, which can be done in a microsecond by this computer. How about for 100 cities? Any idea? Come on, we're all programmers. Give me a number. 3 years. 3 years. That's more than most people would say. Any other numbers? Come on, programmers, how long would it take?
I'd say longer than a snail walking a light year.
Longer than a snail walking a light year. That's longer than 3 years. Go on. How long? Okay, so let's calculate it. Not hard, let's calculate it. Guess how long? You ready? Let's calculate 100 factorial. That's what 100 factorial looks like. Okay, I just want to explain to you. When you multiply by 10, you're adding a digit. When you multiply by 100 times 99 times 98 times 97, each time you do that, most of the time you're adding 2 digits. Not 1 digit, 2 digits. So you have a lot of possible routes. By the way, a lot of those numbers that you're multiplying are going to be tens, so you're going to end up with a lot of zeros. Okay, so how long is that? If you have a computer that can check 1 million paths in a second, I told you this one can do 1 million paths in a second, which means it could do 720 paths in a microsecond. So how long would it take? So I showed you the number of possible routes. Now let's ask how long will it take to go through all those possible routes to find the best? Okay? And the answer is, you divide that giant number by 1 million, you get this many seconds, which gives you that many minutes. Divide by 60 gives you that many hours. Divide by 24 gives you that many days. Divide by 365 gives you that many years. Divide by 100 gives you that many centuries. So it's 2.9 times 10 to the 142 centuries, not to find the answer. By the way, the 3 years was, I've taught this class before, I've never gotten more than 2 weeks. So that's pretty good. You have an intuition. I never ever got more than 2 weeks. So that's pretty good. Okay, so this is an essential limitation of our ability to know. Okay? Now, hold on one second. Don't move. Sorry, advertisement. It's important. Hold on. Okay. So I wrote this book, a very good book. It's called The Outer Limits of Reason, What Science, Mathematics, and Logic Cannot Tell Us. And in it, a part of this is what computers cannot do. And yes, computers can find the answer, but that's a very long time. That's longer than how long it will take me to pay off my mortgage. I mean, that's really bad news. Okay, so you ready? Yes, quantum computers can do an amazing amount of things. By the way, quantum computers can't solve this. Not in a shorter time, nothing. It can't do this. It's just too big of a problem. So there are always harder and harder problems that it would take to do this. Okay, so whenever I teach this, I always get a few responses. They say, don't worry, computers are going faster. We're going to get this stuff that's much faster. And that's true, okay? I grew up on J and 17th. Under my bed in my mother's house is my TRS-80 from 1980. And I can tell you that this computer runs 10,000 times faster than my Radio Shack computer. Okay, she wanted me to learn how to program, so I learned how to program. Okay, so it's not strange. I'm a young man. I live in my mother's house a few years ago, whatever. But it's not strange that in 5, 10 years, computers will go 10,000 times faster. So it might be a good answer to do that. But let's just figure out what with the numbers. Beforehand, we need 2.9 times 10 to the 142 centuries. Now, if we could do it in 10 years with computers that work 10,000 times faster, we only need 2.9 times 10 to the 137 centuries. Okay? What I'm trying to say is faster computers are not going to help you. Yes, that is 1/10,000th of what the other one is, but it's still humongous. These numbers are humongous. Okay. Okay, now, if you look at this computer, it says duo processors. What does that mean? That there's 2 processors running on this thing. Great. So let's have not one computer solving the traveling salesman problem for 100 cities. Let's have 100 or 10,000 processors doing it. Okay? Now I'm going to speak your language. Ready? Let's upload the problem onto the cloud and let volunteers download the problem and then solve it. Okay? And we can get 10,000 people to download the problem. And so that will help us because we're going to do it with 10,000 processors. Again, that will save us. That'll give us 1/10,000th. 1/10,000th of 10 to the 142 centuries is 1/137 centuries. It doesn't help us. Okay. Okay, now here's just a little footnote. Physicists tell us that there are 10 to the 80 particles in the universe. I don't know where they get it. I didn't count it. Okay, Mrs. Avogadro counted Avogadro's number, but whatever that means. 10 to the 80. If every particle in the universe was a computer, then it would only take 10 to the 62 centuries. Okay, so you have it done very easy. If every single particle was working on your computer, this is every programmer's dream. I want a bigger computer. I want a better computer. I want more computing power. If every particle in the universe was a computer working on this problem of solving it, it would only take 10 to the 62 centuries. Okay, another possible solution, quantum computers. Okay. Quantum computers will help. 10 to the 142, the square root of that is 10 to the 71 centuries using Grover's algorithm. So yes, quantum computers will speed it up a lot. You get from 10 to the 140 centuries to 10 to the 71 centuries, you can't solve that problem. And by the way, it's not a strange problem. That's the main point. It's not an unnatural problem. I'm a traveling salesman. I want to travel to 100 cities in 1 year, spend 3 days in each one. I want the shortest route. It's a very nice question. Okay, main point. There are very hard problems even for quantum computers. Okay, what about finding a better algorithm? Okay, as developers, not engineers, this is what gets us. The answer to the traveling salesman problem is let's find a better algorithm that does it. Faster computers are not going to work. Hardware is not going to work. More processors are not going to work. Find a better algorithm. There's been a search for such an improved algorithm for almost 50 years to no avail. Nobody's been able to find it. It probably does not exist, but no one's proved it yet. This is called the P is equal to NP problem. Traveling salesman problem is an example of a large class of, okay, fine. Anyways, we're going to go through this a little bit quickly. Summing up, ready? Quantum algorithms use superposition and entanglement to solve problems. There are some amazing quantum algorithms that solve problems in a short amount of time. There probably do not exist polynomial time algorithms for NP-complete problems. There's a formidable physics engineering challenge to create large-scale quantum computers. We will probably get there. And when we do, RSE will be useless. But there are other harder problems than factoring that will be used to get computational security. The future is unfathomable. That's what makes this topic so fascinating. Okay, thank you. Okay, where to learn about this? Hold on, where to learn. So you go to my webpage, there's a nice little article called An Introduction to Quantum Computing. Very readable, nothing needed whatsoever. So you just go to my webpage, you'll find it there. Okay, this book, it's the top 5 books on quantum computing, whatever. This is the only one readable.
Why is it not number 1?
It's because the 2 morons, well, okay. Can we shut this video? Okay, never mind, hold on, sorry. Okay, that line has to be you. Okay, and this book has a lot. It has a chapter on quantum mechanics and shows you how strange and how wild of a thing it is. Okay, so that takes care of that. I just want to make one advertisement. So I just came out with this book. It's called Moccasin Charts. Okay, it's a very nice. It has every single sugya in Maccas mapped out. I showed it to a Rebbe of mine, and he looks at it and he says, with despair, he says, Gemara for computer programmers. Everything is so exact. It's nicht the way we learned it. No, anyways, but I think you'll appreciate it. It's a nice book. Anyways, we're doing this the modern way. I don't have any books. When I published this book, the publisher gave me 10 copies of this book. My mother took 9 of them. She did. She said, you have many uncles. I have to show that they're not an idiot. Okay. Anyway, so she took 9. This is my only copy that I ever had. So I can't, give away this or sell this. But anyways, it's available on Amazon. You take a pic. Nowadays, you take a picture and you can get it. Anyways, I'd like to thank you all for coming. I'd like to thank my mother for coming and for training me, and thank my wife, et cetera, et cetera.